Hello everyone. Here we will do a tutorial of the analysis of Gaussian Beam in PlanOpSim. So therefore we will make a meta component, but for a meta component we first need a meta cell. We made a dummy meta cell, already created it. We go through here a homogeneous layer with a height of silicon oxide and a planarizing layer, so we have all same height of metacells. This is just to have a phase sweep. If you look at the simulation, then we have a nice sweep of the phase, so we have directly some metacells that will work. We also made an absorbing metacell. It's just a metacell with a high absorbing layer and here added to the material that it should be highly absorptive. So then we go for a library, we make a metacell group, a dummy metacell, and I already added all these metacell in it. So they will come directly, here they are. So a bunch of metacells to make our meta component. So we go for a meta component, make a new meta component, I will call it Gaussian Beam test. We'll make a small meta component of 100 micron to have a quick simulation. We add the metacell group of the dummy metacells. We add them all to this meta component. And then we make a target. So we add a target. And just a normal target for 550 nanometers, a wavelength, plane wave, incident at 0 degree, and then we add here near field wavefront. We will go for a normal aspheric lens with wavelength 550, a focal point at 500 micrometer, and at the amplitude we will add that it is a circular lens and not a square one. So we add here that it should be smaller than the radius, x squared plus y squared, smaller than 50 square, and we generate it. So here you see that the amplitude is now nice cut off. We confirm this, but now we have to do the design with complex values, so the amplitude and the phase. We wait for the near field wavefront to appear. Okay, this is imported here. We go here, and here it's now optimized for phase. We will change this for complex, so now the amplitude is taken into account. We go to design, we start the design. This will take a little while. That's done. Okay, we go to analysis. Here we will see what's happening when we put through a plane wave. We will first start with showing what happens with a plane wave. So we'll call it plane wave. It's 550 nanometer. The orders of the outgoing conditions is the zeroth order. Metacell accuracy is here only 1, that's because it's just a homogeneous metacell, so we don't need a higher accuracy since it's not a real structure. This is just a dummy metacell. And now we will go to look for near field and far field, and we will look for the focal spot. So we will zoom in for a 5 micrometer spot and use, we go to the 500 micrometer distance. We will do a sweep around it. So say DZ, sweeping from 400 to 600 with 10 micrometer spacing. So then we will here add this sweep variable and we do this analysis. This will take a bit longer. So this simulation has been completed. We see here the amplitude of the near field wavefront is indeed nice and circular. If we show, no, not the side, but the face from the top, we indeed have a circular lens. Now to check if the focal spot is 500 micrometer, we will look to the far field wavefront. Since we have here implemented a Z value, their cross section will give a 2D with a Z and a Y axis. So indeed at 500 micrometer we have the focal spot, and the width is about 2 microns here. So it is indeed a focusing lens at 500 micrometer. Now if we go for Gaussian beam, we will create a new. Here we go, instead of a plane wave, we'll now use a Gaussian beam. We will take a beam divergence of say 0.4. Also just perpendicular incident, so nothing changed there. And now we will do this simulation, a new analysis. Then we can go back to this one and confirm. So the Gaussian beam analysis is done. So for the amplitude now we see that indeed the focal spot is smaller due to the selection of a beam divergence of 0.4. Is a Gaussian beam focusing on the Metalens itself. So the phase shouldn't change, which is true, because a Gaussian beam at this focal spot just has a flat phase profile. Okay, for the far field wavefront, we will look at the cross section, and we see here that indeed the focal spot is slightly shifted forward. Also, it's a bit broader and in both directions. So the broadening of the focal spot is expected directly from having a lower numerical aperture, and having the focal spot slightly shifted forward is unexpected. That's because the focal spot here was really small. It only has about 1 time a 2 pi shift within the Metalens. You could see here, if you go back to the amplitude, it's only the middle part, and that causes the and that influences the focus of a lens. So for this reason, it's useful to directly see a Gaussian beam, what happens with it, how much can we choose to use our light source on the Metalens. Can we underfill it, or should we fully fill it or overfill it? This can give a simulation of that.